Today we're going to be talking about how to deal with rational expressions, in particular identify their domain, and to identify how to simplify it if possible. So let's actually define a rational expression. So as you might recall, a rational number is something that can be written as a fraction. And if we're dealing with a rational function or a rational expression, it's something that is a fraction of polynomials. And just like with rational numbers, where technically whole numbers count, regular polynomials also count since they're being technically divided by 1, but that's considered kind of a boring rational expression. Typically, we're going to deal with more interesting ones where it's a non-trivial polynomial divided by another non-trivial polynomial. However, just like we normally can't divide by 0, we need to make sure that if we have two polynomials, p of x and q of x, being divided, that denominator can never equal 0. So let's take a look at an example of that. So for this very first one, we need to make sure of two things. A, domain-wise, we need to make sure that the denominator does not equal 0. What's the denominator in this case? X plus 2. So in which case am I looking at? This very first example here. So for this very first example here in particular, we need to make sure that denominator does not equal 0. So in particular, the x plus 2 does not equal 0. So x is allowed to be any number except for -2. Because if I were to solve that, how would I undo adding 2? I would subtract 2 to both sides. So x is not allowed to equal -2. So we would say its domain is any real number where x does not equal -2. We'll get into simplification a little bit later here, but keep in mind that the domain applies even before simplification. So even if I can simplify this rational expression, which actually in this case I can, it is the case that no matter what, because on the original I cannot plug in -2, otherwise that denominator would become -2 plus 2 equals 0. That's going to just apply. So I'm allowed to plug in any number except for that one. And let's look at some more examples of where we could run into trouble with that. So let's say you didn't think about that and you were just kind of dealing with this rational expression as is. So for this first function, recall from function notation that if I have f parentheses -1, that means I'm going to replace x with -1. So in this expression that is f of x, everywhere I see an x, I want to replace them with -1. So the expression is f of x is equal to x plus 3 over x minus 4. In this case, I'm replacing x with -1. -1 plus 3 gets us 2. -1 minus -4 gets us -5. And our final solution would be 2 over -5. So far, so good. Similarly, in the next expression, if I'm plugging in 0, you might be thinking, oh my gosh, we're in trouble. We're not allowed to have 0 in the denominator. As long as the denominator does not simplify to 0, we're good. So we actually, if we plug this in, because remember f of x is equal to x plus 3 over x minus 4. In this case, our x is going to be 0. So everywhere I see an x, I'm going to replace them with 0. So in this expression, 0 plus 3 is going to give us 3, 0 minus 4 is going to give us -4, and our final answer is 3 over -4. We're good to go. For the last one, if we double check that one, when we plug in f of x, that means everywhere I see an x, I'm going to replace it with 4 in this case, so f of 4 would be 4 plus 3 over 4 minus 4, and oh my gosh, we're in trouble because we're not allowed to divide by 0. So this is undefined. And in the original expression, you would have noticed that that denominator is not allowed to equal 0. So if x minus 4 cannot equal 0, x is allowed to be any number except for 4. And if you attempted to plug it in, you're going to run into trouble because you're going to start dividing by 0. So whenever you're thinking about the domain of a rational expression, you should be thinking pre-simplification, pre-doing anything at all. I need to make sure that denominator does not become 0 when I plug this number in. How could you most easily solve for that? Set that denominator literally not equal to 0 and solve for x as though that not equal to sign was an equal sign. So let's go ahead and talk a little bit more about that. So that's what this summary is noting here. is that when you're talking about the domain of a rational expression, you want to exclude any values that would make that denominator 0. That's the big idea. So in this next rational expression, if I have 1 over x minus 3, I need to make sure x minus 3 is not 0, so x cannot be 3. If you're doing this in set builder notation, that's actually the nicest way in order to express it, is you just say, okay, 3 is an excluded value, x cannot be 3. If you're going to be using interval notation, it's actually going to be helpful to visualize this on a number line, because number line wise, I'm going to use an open circle on the 3 because 3 is not included. Then it can be anything smaller than 3, anything bigger than 3. And then our final solution would be negative infinity to 3, union 3 to infinity. Now, if that denominator is a quadratic instead of linear, what you're going to have to actually do is factor. And in particular, anytime that you're going to be simplifying rational expressions, you're going to want to factor. So let's take a look at an example here. So if I'm going to factor this first rational expression, well, the numerator is a difference of squares, specifically x squared minus 3 squared. So he's going to factor into x minus 3 times x plus 3. And the denominator, he's going to factor into, this is a case where the leading coefficient is 1 for a trinomial. So we can factor this into what's going to multiply to negative 6 and add to negative 1. That's going to be negative 3 and positive 2. Now you want to note the domain before you start doing any simplifications. So domain-wise, we need, again, that denominator to not equal 0. So I have parentheses x minus 3, parentheses x plus 2 cannot be 0. Now, whenever you have something factored out like this, what you're going to exploit is what's called the zero product property. This is something we're actually technically going to cover during quadratics, but I think it's worth looking at now. If you're not comfortable looking at it right now, go ahead and skip ahead a little bit to the lesson on quadratics. That will be a few units from now, but we can go over kind of the basics from here, that if we have something times something equals 0, or does not equal 0 in this case, then one of those two somethings has to be 0. So that's what we're going to be checking for here, is we need to make sure both the x minus 3 doesn't equal 0 and the x plus 2 doesn't equal 0. That's really the short of it, is that you're going to make sure that you state the domain restriction for each factor in the denominator cannot be 0. In that case, each factor being each thing that's being multiplied. So here we would discover, okay, x cannot be 3, x cannot be negative 2. If you were to express that domain on a number line, what you would do is plot it out that it cannot be negative 2, so you would have an open circle on negative 2. It cannot be 3, so you have an open circle on 3. He could be any number smaller than negative 2. He could be any number between negative 2 and 3. And he could be any number bigger than 3. So your three regions of this are going to be, they could be from negative infinity to negative 2, that first region, or from, and I did not give myself enough room here at all. Let's retry that. From negative infinity to negative 2, or from negative 2 to 3, or from 3 to infinity. So that's worth explicitly plotting out to sort of visualize how that function notation is going to look. However, for the simplified expression, now we're going to note if we ever have something divided by itself. So in this case, x minus 3 divided by x minus 3, that's going to equal 1. So that's why we're able to quote-unquote cancel it out to be left with the simplified expression as x plus 3 over x plus 2. So here, and again sort of in the type notation, same sort of deal. Whenever you have something divided by itself, that's able to cancel out to make 1, but that's still an initial restriction on the domain. So that is still the domain that x cannot be 3 and x cannot be negative 2. Both of those happen pre-cancellation, but then you can cancel out to get that final simplified expression. So let's go ahead and go through that a little bit more in depth. Now, what I personally like to do, despite the directions, is I first factor, then I find the domain before I do my simplification because I don't want to forget about anybody I canceled out. Then we're going to simplify. So that's kind of the general order we're going to use here. So let's check that out for this first one. So for this first one, that numerator is already simplified. That's just x minus 3. The denominator is a difference of squares. Specifically, that's x squared minus 2 squared. So it's going to become x minus 2, x plus 2. Then for the domain, we need to make sure each factor cannot be 0. So x minus 2 cannot be 0, and x plus 2 cannot be 0. So in particular here, x cannot be 2 by adding 2 to both sides, and x cannot be negative 2 by subtracting 2 from both sides. And if you were going to write that in formal set builder notation, you would toss on the x such that, and then your little curly braces, call it a day. Those are the two numbers that x is not allowed to equal. In order to put that in interval notation, what you would do is visualize on a number line. We've got negative 2 and 2 in terms of the order. Open circles on both of them, and it can be any number smaller than negative 2, any number between negative 2 and 2, and any number bigger than 2. So your interval notation would be negative infinity to negative 2 to 2, and 2 to infinity. All three of those regions would count, and that would be your final domain. In terms of simplification, this guy has no common factors, so he actually doesn't simplify. There's no case where I have something divided by itself, so we're just going to call it good. That's an already simplified problem. Let's go ahead and try out the next one. So for the next one, we have 4x minus 1 over, and then that denominator, again, we want to factor him. So here we're trying to multiply negative 12 and add to negative 1, and since the leading coefficient is 1, we can jump straight to our parentheses. So he's going to factor into x minus 4, x plus 3, since negative 4 times positive 3 gets us negative 12, and negative 4 plus positive 3 gets us negative 1. Now we're going to note the domain. And for the domain, we again need both of these factors not to be 0, otherwise we're going to end up dividing by 0. So we need x minus 4 cannot be 0, and x plus 3 cannot be 0. For the first one, we're going to add 4 to both sides, so we get x cannot be 4. The second one, we're going to subtract 3 from both sides, so we get x cannot be negative 3. Then we build our set builder notation, so x such that x is not equal to negative 3 or 4. That's how you would note it in set builder notation, and that line up and down just means such that. If you want more review of that, feel free to check out the video on how to do inequalities, so we go over a lot of that notation there. In order to then turn it to set builder notation, you want to note that we are not allowed to equal negative 3 or 4, so they get open circles, but anywhere else on the number line is okay. So that means that we can go from negative infinity to negative 3, from negative 3 to 4, from 4 to infinity. And notice how all of them get parentheses because we cannot equal those numbers. And really, that's just a fancy way of trying to say skip over the numbers negative 3 and 4, because if I plug those in, that would make that denominator 0. But any other number in the universe is okay. So I'm going to encourage you to go ahead and pause your video and try these next three yourself, and then unpause your video to compare with what we get. So for these next three, both the numerator and denominator need to be factored. So for the first one, for the numerator to be factored, we're trying to multiply to positive 3 and add to negative 4. So that's going to be x minus 3, x minus 1. For the denominator, that's a difference of squares, which is x squared minus 1 squared. So that's going to be x minus 1, x plus 1. In order to find its domain, which I would recommend doing next, you want to make sure that neither of your factors equal 0, so x minus 1 cannot be 0 and x plus 1 cannot be 0. For the first one, add 1 to both sides, so x cannot be 1. For the second one, subtract 1 from both sides, so x cannot be negative 1. So if we're going to use set builder notation, that would be x such that x does not equal negative 1 or 1. If we're going to be using interval notation, that's going to be any number smaller than negative 1, but not including the negative 1, any number between -1 and 1, but not including either of those, and then any number bigger than 1 is going to count as well. Now we're ready to go ahead and simplify. So for the simplification, will anything cancel out? Well, x minus 1 divided by x minus 1 does indeed make 1, and we're just going to be left with x minus 3 over x plus 1 as our final simplified form. But remember, in terms of that domain, we still can't plug in x as 1 because of that pre-simplified form. Let's go ahead and go over the next one. So for the next one, we also have to factor him. That numerator is going to factor into, we want to multiply to positive 3, add to negative 4 again, so we're still going to factor into x minus 3 over x minus 1. For the denominator this time, we're going to multiply to positive 5 and add to negative 6, so that's going to be x minus 5 times x minus 1. Now we're going to look at the domain. Notice how for the domain we never care about the numerator. You can do 0 divided by a number, but you cannot do a number divided by 0. So for the domain, you always need to make sure all factors in the denominator do not equal 0. That's really the key part. So for this first one, we're going to add 5 to both sides to get x cannot be 5. The second one, you're going to add 1 to both sides to make sure x cannot be 1. So in set builder notation, that would be x such that x does not equal 1 or 5. In interval notation, that would be noting any number smaller than 1, or any number between 1 and 5, or any number bigger than 5 are all considered part of the domain. To simplify the function, if you look at the original, do I have anything that's going to cancel out? Yes, I do. X minus 1 divided by x minus 1 makes 0. And I would be just left with x minus 3 over x minus 5 as our final simplified form of the function. For this last one, the factoring itself is going to get a little bit more complicated with both of these because they have a leading coefficient. So I'm actually going to factor them off to the side. For the very first one, you want to multiply to 3 times 2 because that's a times c, so multiply to 6 and add to 5. We're going to break up that middle term, therefore, into 3x squared plus 3x plus 2x plus 2. So notice before, the question was the other way around. We wanted to multiply to 5, add to negative 6. Here, because we did 3 times 2, we're going to multiply to 6 and add to the middle, which is 5. Then we're going to find our greatest common factor of each group. The greatest common factor of 3x squared and 3x is 3x. 3x squared divided by 3x gives us x. 3x divided by 3x gives us 1. The greatest common factor between 2x and 2 is 2. 2x divided by 2 is x. 2 divided by 2 is 1. And now we're going to have one parenthesis of what they have in common, which is x plus 1. And one parenthesis of what's left after you divide out that x plus 1, aka what's different, which is your 3x plus 2. So we've got, for our numerator there, we've got x plus 1 times 3x plus 2. For the denominator, we're going to do a similar sort of thing. So we have 3x squared minus x minus 2. This time we're going to multiply to negative 6 and add to negative 1. So we're instead going to use the numbers negative 3 and positive 2. So we're going to split the middle term into negative 3x plus positive 2x. Drop down the other terms. Now we want to use factoring by grouping. So for the first two terms, their greatest common factor is 3x. What will be left in parentheses? Well, 3x squared divided by 3x leaves us with x. Negative 3x divided by 3x leaves us with negative 1. For 2x minus 2, their greatest common factor is positive 2. 2x divided by 2 leaves us with x. Negative 2 divided by 2 leaves us with negative 1. And then our final parentheses will be what they have in common, which in this case is x minus 1. And then what is different, what would be left after factoring out that x minus 1, which is 3x plus 2. So I'm going to write that as my other parenthesis. And again, we still want to figure out domain pre-simplification, so we're going to go ahead and figure that out now. We need each factor in the denominator cannot be 0. So we need x minus 1 cannot be 0, and we need 3x plus 2 cannot be 0. For x minus 1 cannot be 0, I'm going to add 1 both sides. We're going to get x cannot be 1. For 3x plus 2 cannot be 0, that's going to be 2 steps. So first I subtract 2 from both sides. 3x cannot be negative 2. Then I divide both sides by 3 to undo multiplying x by 3. So then you're going to get x cannot be negative 2/3. Then in terms of set builder notation, that would be x such that x does not equal negative 2/3 or 1. In terms of the number line, that would be that x can be any number smaller than negative 2/3, any number between negative 2/3 and 1, and any number strictly bigger than 1. That would be your full set builder notation. In terms of simplifying the original, you should notice that 3x plus 2 divided by 3x plus 2 is going to make 1. So our final simplified function would be x plus 1 over x minus 1. So here's our domain, written two different ways, and here's our simplified expression. So to recap, you always want to find domain pre-simplification. What you want to make sure is the denominator does never equal 0, and if you have more than one factor in the denominator, that means that you have to make sure each and every factor cannot be 0. In order to write that in interval notation, it can help to visualize on a number line, where those numbers it is not allowed to be equal to would have open circles, and every other region of the number line would be shaded in, which is why you end up with this interval notation that basically says every number smaller than one of these numbers, every number between these two numbers, and every number bigger than this other number. If you had 3 numbers that couldn't equal, I would definitely recommend visualizing that on a number line, because you're going to get a lot more regions, because you're essentially doing a fancy way of saying any number in the universe except for these particular numbers I just found that would make that denominator 0. After you've found the domain, then you're ready to simplify. You can simplify if you have the same factor being repeated on the top and the bottom, aka you have two things that when being divided would divide to make 1. So you're looking for those repeat factors. So like this example had it, these other two examples had it, but our first two examples did not have it. There were no factors that would cancel out. There was nothing that would make 1. 4x minus 1 divided by x minus 4, that doesn't make 1, that's just its own thing. Versus if I had another x minus 4, another x minus, or x plus 3, in the numerator, then I could cancel stuff out. Or if I had a 4x minus 1, the denominator, again, stuff would cancel out. But I don't, so that's just good to go. Now, just as a quick note, that if hypothetically that 4x minus 1, for example, in problem 2 had canceled out, you would still have a 1 left there on the numerator, because again, you're doing division for that canceling out, quote unquote. So if everything on either the top or the bottom cancels, that top or the bottom will just have a 1 left over, because 1 is what is neutral in terms of multiplication division.